Alright, so in the last part of the video, we established these two equations. First, from implementing theta 1 into the Lagrangian equation, and the second by implementing theta 2 in the Lagrangian equation. So this here from theta 1, this here from theta 1, and this here from theta 2. Now, before we so what we're gonna do here by using these two equations is we're gonna establish our values for theta 1, the angular acceleration of theta 1, so theta 1 dot dot, and theta 2 dot dot. But before we do that, there are elements in these equations that we could simplify, and so we're gonna do that first. Let's say this here is equation 1, and this here is equation 2. Let's look at equation 1 first. In equation 1, we see that all of the terms has L1 in it. So this term here has L1, 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 and L1. And so what we're going to do first, so for number 1, we're going to divide everything by L1. And so we get M1, theta 1 dot dot, L1 squared becomes just L1, plus M2, same thing, plus M2, theta 2 dot dot, L2 cosine, minus, from this here we get rid of the L1 and we get M2, theta 2 dot L2 sine of theta 1 minus theta 2 times theta 1 dot minus theta 2 dot. And we're going to add M2, theta 1 dot, theta 2 dot, L1 is cancelled, so we have L2 sine of theta 1 minus theta 2 plus G L1, no, plus M1G sine of theta 1 plus M2G sine of theta 1 equals to 0. Now, let's look at this here, this part over here. When we imagine expanding this term out, we're going to have minus M2 times theta 1 dot, theta 2 dot, L2 sine theta 1 minus theta 2, and plus M2 theta 2 dot squared, L squared, sine theta 1 minus theta 2, if we expand this term over here, because we multiply this here by that, and this here by that, and get the minus. And the first term, which is M2 theta 2 dot, L2 sine theta 1 minus theta 2, that's identical to this here. So this part here, when we expand it, is oppositely and identical to this here. But it has a minus sign. And so we know that these two terms can be cancelled out, or should I say, just we add something and we minus something. We get rid of the two terms, because they're positive and minus, but with the exactly same value. And so let's cancel that out. Let's erase that here, all of that here, and this here. Then what we are left with is plus M2 theta 2 dot squared L squared sine of theta 1 minus theta 2. And what we also know is that for these two terms, the same term here is repeated. And so we could wrap these two terms with this value. And also for these two terms, we could wrap them by this value, G sine theta 1. And after we do that, we're going to have, well, when we wrap these by theta 1 dot dot L1, we're going to have M1 plus M2 of theta 1 dot dot L1. That's this here done. this we just leave it as it is. So m2 theta 2 dot dot L2 cosine of theta 1 minus theta 2. We had plus, because it's a minus times a minus, so plus m2 theta 2 dot squared, because theta 2 dot we're multiplying everything by theta 2 dot. So we're multiplying a term by theta 2 dot. So plus theta 2 dot squared L2 sine of theta 1 minus theta 2. And then we have these two terms. Again, we can wrap them up with g sine theta 1 and get m1 plus m2 of g sine of theta 1. And that we know is going to be equal in value to 0. All right, so that's our new equation 1. That's our new equation 1. So we have basically simplified this long equation to a rather simple one, but which is still not that simple. But that's, that's the simplest term we could get, the simplest form of this equation that we could get. So now let's get rid of this here and look at the equation over here, equation 2. Equation 2, we could do, let's look at it first. We see that every term has m2 and L2 in it. m2, L2, m2, L2, m2, L2, m2, L2, and m2, L2. And so we could divide everything by m2, L2, and there wouldn't be any problem. So let's do that first. We're going to get theta 1 dot, theta 2 dot, L1 sine of theta 1 minus theta 2 minus g sine of theta 2 minus theta 2 dot dot times L2, because it's squared, we only get one L2 left, minus theta 1 dot dot L1 cosine of theta 1 minus theta 2 plus theta 1 dot L1 sine of theta 1 minus theta 2 times theta 1 dot minus theta 2 dot is equal to 0. Now, we have the same problem with this term being multiplied, and we could see that the same term is repeated over here, a very similar term. So we have this over here, which is theta 2 dot times this over here. So this here times theta 2 dot, which is here, is going to be equal to that. And we have theta 2 here. And luckily it's a minus. And so, as we did before, we could cancel them out. This is a plus theta 1 dot, theta 2 dot, blah, blah, blah. This is a minus theta 1 dot, theta 2 dot, blah, blah, blah. And so we could basically say, okay, so that here is going to cancel out. It's this term here. And only get theta 1 dot squared L1 blah, blah, blah left. And so that's it. We have, when we do that, we have minus g sine, all of these the same as it was. But here we're going to have theta 1 dot squared L1 sine of theta 1 minus theta 2, and that's going to be equal to 0. Now, we see that now we could erase all this, because this is our new form. And we have equation number 2. So let's erase this too. Right, so now we have our simplified equations of motion, but we still haven't defined them in terms of theta 1 dot dot and theta 2 dot dot. Now, let's look at this equation here. It's rather simple, and what's good about this equation is that, it's simple. And so we could get a fairly simple term in terms of theta 2 dot dot, but still we're gonna have theta 1 dot dot in it. But what's good about it is that it's simple. So for the value we get in terms of theta 2 dot dot, if we implement that value into this equation, we're gonna get our desired equation of motion in terms of theta 1 dot dot. And in the coding, in the simulation, when I'm going to code later, I'm going to basically get, okay, I have my value for theta 1 dot dot. If I put that value into the equation I have for theta 2 dot dot, I'm going to get both values. Doesn't really matter whether I get an equation both for theta 1 dot dot and theta 2 dot dot, all in terms of variables that are not theta 1 dot dot and theta 2 dot dot, because if I know that, I can just use that value into this value and it won't change my results. And so I'm going to do that. And in order to do that, I'm going to first get a value in terms of theta 2, a value that's given for theta 2 dot dot. So when I rearrange this equation in terms of theta 2 dot dot, I'm going to have, well, theta 2 dot dot to that side. So theta 2 dot dot L2 is going to be equal to theta 1 dot squared L1 sine of theta 1 minus theta 2 minus g sine theta 2 and minus theta 1 dot dot L1 cosine of theta 1 minus theta 2. Just checking if it's right, I did it correctly. Yeah, I think I did. All right, so we get theta 2 dot dot then is going to be equal to that divided by L2. So that's going to be our equation for theta 2 dot dot. But still, as I said before, we have theta 1 dot dot in it, and so we're not quite finished. What we're going to do is implement the value I get here into this equation, into this long equation, and get a new equation that gives my value for theta 1 dot dot. All right, so let's do that here on the top. So for me to do this, I'm going to have to rearrange everything in terms of theta 1 dot dot. Right, so first of all, let's write everything down after substituting theta 2 dot dot with this value. So theta 1 dot dot L1 plus M2 L2. Now, we have theta 2 L2 here. And we know that theta 2 L2 is equal to the numerator of this fraction, this value. And so, if we multiply this here by M2 cosine of theta 1 minus theta 2, we're going to get what we need. And so let's do that. We have M2 cosine of theta 1 minus theta 2, and we're going to multiply that value by our long denominator, which is given as theta 1 dot squared L1 sine that minus g sine theta 1 dot dot. We have our theta 1 dot dot, so we have two expressions, two terms that has theta 1 dot dot in it, and get minus theta 1 dot dot L1 cosine of theta 1 minus theta 2, bracket closed. And then we have, what we have is this here. Plus M1 plus M2 of G sine theta 1 is equal to 0. All right. Okay. M2 cosine theta 1 minus theta 2. Yeah, it looks all right. Right, it looks all right. And now what we're going to do is expand this here. So let's expand this here for now and get M2. We'll write these down and the sines and cosines at the last because that looks better. We're going to have this here, M2 times theta 1 dot squared L1, and get the sines and cosines. All right. And then we are going to expand this over here too. So get minus M2G sine of theta 2 cosine of theta 1 minus theta 2. Now we have our theta 1 dot dot, which is very important. We have M2 theta 1 dot dot minus M2 theta 1 dot dot L1 and cosine squared of theta 1 minus theta 2 because we have two cosines theta 1 minus theta 2. And the else is going to be same. And you could imagine all of this here being replaced by our new value on the bottom. Alright then, we have, let's wrap this term here and this term here by theta 1 dot dot. That's going to give us theta 1 dot dot of, look at this first, M1 plus M2 of L1 minus M2 of L1 of cosine squared of theta 1 minus theta 2, bracket closed, is going to be equal to a very, very long term. So we have used that and that. So let's write this term here because it's negative, so it's going to be converted into a positive. So let's write that one first. We're going to get M2 G sine theta 2 cosine minus that, which gives us minus M2 theta 1 dot L1 so we are squared sine of theta 1 minus theta 2 cosine of theta 1 minus theta 2 and everything else. Minus, plus, minus, minus, and minus. And so, consequently, our value for theta 1 then must be equal to this divided by this value here. So I'm going to write that first. Minus M2L1 cosine squared of theta 1 minus theta 2. Yeah, and erase this term here, we get our value for theta 1 dot dot. And we see that for theta 1 dot dot, we don't have anything, we don't have theta 2 dot dot in it, which states that the method worked. And so that's basically theta 1 dot dot as this, but when we compute this with our, I don't know, whatever, MATLAB, with MATLAB, we're going to get a value for theta 1 dot dot, and implementing that value into this equation here, we're going to get another value for theta 2 dot dot, which basically defines our accelerations, our two angular accelerations that we need to simulate the system. Yeah, that's pretty much it. One more addition that I would make is that I'm just going to erase all this. Now we have used it. It would be even more convenient if we go on and let's wrap some values that, for convenience, let's say this is going to be equal to a long expression. Let's wrap everything here by L1, because when we code, it's good to wrap things because that makes our lives easier. Because we reduce the number of multiplications we have to do. So we have M1 plus M2 minus M2 cosine squared of theta 1 minus theta 2. And we could get rid of the bracket here. M1 plus M2 minus M2 cosine squared theta 1 minus theta 2. And for the top, let's see. We could wrap everything by M2. Wrap these three by M2 and leave this as it is. That would be what I would do is, or by sine theta 1 minus theta 2, or cosine M2G, sine theta 1 minus theta 2, and 2 Well, let's wrap it by M2. So we get, cosine, what's cosine be? But this is what I'm going to do. I'm going to wrap everything by M2 and get G sine theta 2 cosine of theta 1 minus theta 2 minus theta 1 dot squared L1 sine of theta 1 minus theta 2 cosine minus, let's just leave it like this. And I'm gonna do a similar thing when I code. But yeah, that's basically it. This is my first equation for theta 1 dot dot, and for theta 2 dot dot, I'm gonna have theta 1 dot squared L1 sine theta 1 minus theta 2 minus G sine of theta 2 minus theta 1 dot dot, which is this value here, L1 cosine of theta 1 minus theta 2 over L2. That's going to be the two equations that's going to define our pendulum system, which looks very simple. So for a system that looks like that, whereby this is theta 1, this is theta 2, this is L1, this is L2, this has a mass of M1, this is a mass of M2. We define our system as such. And now in the next part of the video, I'm going to move on to using this equation into my coding system, my MATLAB, and hopefully we would be able to simulate this pendulum system, and we're going to see the masses moving in a very chaotic way, but which looks like there's no rule, but as you can see here, there is some kind of rule. That is very complicated, but it is solvable, and that's what makes physics so entertaining and fun. Is that even such chaotic systems like a double pendulum, looks like there's no set rules governing this system. It looks so chaotic, but at the end of the day, there is something that governs and predicts how it will move. And yeah, that's the purpose why I'm doing this. And yeah, hope I see you in the next video where I'm gonna code. I'm gonna make a code for this simulation. Thank you very much for watching and see you in the next video. Thank you.